Centripetal acceleration. We've seen a lot of videos on YouTube with the derivation of this formula here, v squared on r, being the centripetal acceleration that keeps a particle in circular motion, and it's got to be uniform circular motion in this case, where the actual speed of rotation is constant. But what's changing here is the velocity, and the velocity only changes in direction. The magnitude of the magnitude of the velocity is always the same, just the angle is changing. Now, in a lot of derivations, they present vectors, like for example, the top vector would be v0, the 0 being the vertical component, which in this case is 0, and the v at the front here is the horizontal component. And the next vector here would have to take into account the angle, theta. So in fact it's actually v cos theta minus v sine theta. And the reason it's negative for the vertical component is because it is in that direction, downwards. Now my physics teacher in high school derived this formula, and it was really complicated, you know, subtraction of the vectors and working out the time, blah blah blah. And I think it went over most of our heads, really. There are simple ways to think of this. The simplest way, well, one simple way. I'll show one simple way, and then I'll show an even simpler way. If we think of the vector of the at the top of the wheel here, and we think of a vector here, and we think of a vector here, and think of a vector here. So the vector, always the same, v, v, v and v, only changing in direction. If we just think of the vector itself, we have the start vector here, and then as the wheel rotates, the vector changes. This is just the vector of the velocity. Don't worry about its position on the wheel, we're just talking about the vector itself. So we think of it all starting at the one point, and as the wheel rotates, the vector just keeps changing direction until eventually, when the wheel is completely rotated, the vector has changed direction by 360 degrees. We're all the way around. So we can say the change in the velocity is just the change in the direction, which will be for the full circumference of the circle. It's just going to be 2 pi v, and that will be the actual change of the velocity. Now the time is just the time it takes a wheel to go around once. The time it takes to go around once is just 2 pi r, which is the circumference of the circle, divided by the velocity, or the speed in this case, because it'll just be constant speed as it rotates. So you just, the acceleration is just change in velocity, change in time, which equals 2 pi v on 2 pi r divided by v. So the 2 pi's cancel, and what we end up with is v squared on r. How simple is that? If that is a little bit difficult to follow, there is another way. We can think of the circle here, and we just take two vectors, one here, v, one here, and this will be minus, it's still direction. So the delta v in this case is 2v. That's easy enough. Goes from plus v to minus v. Now, we're not considering all the vectors, we're just considering two vectors. So what we have here is 2r, there's the distance between the 2 points. Okay, now, because we're considering just two vectors, the delta t will just be 2r divided by the velocity. Because we're not considering it moving around a circle, we're just considering two vectors. If you ignore the circle, it'll just look like this. V, V, with the distance between them 2r. Okay, that's the only information you have. Forget the circle. If this is the only information you have, these will be the delta v and delta t. So the acceleration is delta v on delta t, which equals 2v divided by 2r on v. So the 2's cancel out and we end up again with v squared on r. So I hope that sort of simplifies the derivation of the centripetal acceleration quite a bit. For all you high school kids out there, I hope you enjoyed watching the video and it does help you. So thanks for watching. Bye bye.